For over a century, telecommunications relied on a specific mechanical constraint. Every voice required a continuous, physical circuit of copper wire to reach its destination. This thick, braided cord trailing from early telephones illustrates the pre-1973 paradigm. You did not call a specific person. You dialed a geographic location, a building physically tethered to an electrical grid. That architectural dependency remained the standard until April 3, 1973. Motorola engineer Martin Cooper developed this prototype as a brute force engineering solution to a complex wireless transmission problem. The lower chassis reflects the hardware required for the era. The device weighed 2 kilograms and required 10 hours of charging to yield exactly 30 minutes of continuous transmission capacity. These specifications represented the physical limit of 1973 hardware. Severing the copper wire required this exact scale of battery density and signal amplification. Examine this 1970s Manhattan streetscape. For a wireless signal, this environment is an obstacle course of dense concrete and steel framing. Modern cellular networks transmit efficient digital packets, but 1970s voice transmission relied on a continuous analog radio frequency wave. Sustaining that wave requires a high, uninterrupted draw of electrical power. Engineers faced the reality of signal attenuation. Following the inverse square law, an analog wave rapidly loses strength as it penetrates dense urban structures. Pushing a signal through concrete without modern integrated circuits required heavy, localized amplification. The physical dimensions of these analog circuit boards determined the bulky shape of the upper chassis. True geographic autonomy meant shrinking the transmission power of a localized radio tower down into a handheld device. Powering those large analog boards required a substantial energy source. The lower half of the chassis consisted entirely of nickel-cadmium battery cells. The engineering constraint was energy density, the amount of electrical energy stored in a given physical volume. Transmitting a continuous analog frequency is taxing. 30 minutes of continuous conversation completely drains the capacity of these cells. To recharge, the heavy particles inside the cells had to migrate across porous chemical membranes, a process that took 10 hours to reverse the 30-minute depletion. To guarantee a 30-minute transmission window, engineers had to increase the physical volume of the batteries, creating the 2-kilogram mass. That heavy battery block was the unavoidable physical cost of 30 minutes of mobility. Because of high power demands and low battery densities, 1970s industry consensus held that a mobile phone required a vehicle. AT&T's models sidestepped the battery bottleneck by using a car's engine to generate electrical power for the radio transceivers. The telecommunications establishment viewed a standalone, battery-powered personal node as a physical impossibility. Cooper tested that assumption directly. Standing on a sidewalk in Midtown Manhattan, he placed a call to his rival at AT&T. The call provided empirical proof that an autonomous, non-vehicular node could successfully interface with the established cellular grid. That transmission proved that personal mobility was a viable engineering target, regardless of vehicular support. Cooper's prototype reoriented global telecommunications R&D, accelerating the development of cellular infrastructure and component miniaturization. Over the next 50 years, heavy analog boards and nickel-cadmium blocks were replaced by digital RF modems and high-density lithium-ion cells. The 1973 call redirected network development away from wiring physical locations toward connecting mobile individuals. While chemistry and digital signals have evolved significantly since 1973, every modern smartphone is still fighting the same engineering battle, maximizing connectivity while minimizing physical mass.